Mastering Time. Unleashing the power of time series analysis and forecasting. Welcome everyone. Today we will be discussing one of the most important topics in data analysis: time series analysis and forecasting. This is a technique used to analyze data that changes over time, and it has a wide range of applications in many fields such as finance, economics, and engineering. For example, imagine you are running a business and you want to predict how much inventory you will need for the next year. Or, suppose you are an economist trying to forecast the GDP growth rate for your country. These are just a few examples of the importance of time series analysis and forecasting in our daily lives.
What is time series analysis? Time series analysis is a statistical method used to analyze and forecast the behavior of a variable over time. This technique is widely used in various fields such as finance, economics, engineering, and many others. The main objective of time series analysis is to identify patterns or trends in the data and use them to make informed predictions about future behavior. For example, time series analysis can be used to forecast stock prices, predict customer demand for a product, or estimate the impact of a policy change on an economy. One of the key reasons why time series analysis is important is that it allows us to make predictions based on historical data. By analyzing past trends and patterns, we can identify factors that influence the behavior of a variable and use them to forecast its future behavior. This can help individuals and organizations make informed decisions about investments, production planning, and resource allocation. Without time series analysis, it would be difficult to make accurate predictions about future events and trends. Components of time series. Time series data can be broken down into three main components: trend, seasonality, and noise. Trend refers to the long-term pattern of the data, whether it is increasing or decreasing over time. Seasonality refers to any regular pattern that occurs at fixed intervals, such as daily, weekly, or yearly cycles. Noise, also known as random variation, refers to any unpredictable fluctuations in the data that cannot be explained by the trend or seasonality. To illustrate these components, consider the example of monthly sales data for a retail store. The trend might show a gradual increase in sales over time due to overall business growth. The seasonality might reveal spikes in sales during holiday shopping periods like Black Friday or Christmas. Finally, the noise might represent unexpected dips or surges in sales due to factors like weather, economic conditions, or supply chain disruptions. Time series models. Time series models are mathematical models used to analyze and forecast time series data. There are several types of time series models, including ARIMA, exponential smoothing, and neural networks. ARIMA models are commonly used for modeling time series data with trend and seasonality components. Exponential smoothing models are useful for modeling time series data with a smooth trend component and little to no seasonality. Neural network models are powerful tools that can model complex relationships in time series data. Each model has its own strengths and weaknesses, and the choice of model depends on the characteristics of the data being analyzed. For example, if the data has a clear trend and seasonality, an ARIMA model may be appropriate. If the data has a smooth trend and little seasonality, an exponential smoothing model may be more suitable. Neural network models may be useful when the data has complex relationships and patterns that cannot be easily modeled by other methods.
ARIMA model. The ARIMA model, or Autoregressive Integrated Moving Average Model, is a popular method for modeling time series data. It combines three components: autoregression, differencing, and moving average. Autoregression involves using past values of the variable being modeled to predict future values. Differencing involves taking differences between consecutive observations to remove trends and seasonality from the data. Moving average involves using past errors in the predictions to improve future predictions. By combining these components, the ARIMA model can capture complex patterns in time series data. To select the appropriate parameters for an ARIMA model, it is important to understand the characteristics of the data being modeled. The order of the autoregressive, differencing, and moving average components can be determined by examining the autocorrelation and partial autocorrelation plots of the data. The number of terms for each component can be determined by examining the AICA Information Criterion, AIC, and Bayesian Information Criterion, BIC, for different models. Once the appropriate parameters have been selected, the ARIMA model can be used to make predictions about future values of the variable being modeled.
Exponential smoothing model. Exponential smoothing is a popular time series forecasting method that uses a weighted average of past observations to predict future values. The weights assigned to each observation decay exponentially as the observations get older, hence the name exponential smoothing. This technique is particularly useful for data with no clear trend or seasonality. To use exponential smoothing, we must first select the appropriate smoothing parameter, which determines how much weight is given to recent observations versus older observations. There are different methods for selecting this parameter, such as trial and error or using statistical techniques like maximum likelihood estimation. Once the parameter is selected, we can use the exponential smoothing formula to forecast future values based on past observations.
Neural network model. Neural networks are a type of time series model that can be used to make predictions based on historical data. They are particularly useful when the relationship between inputs and outputs is complex and nonlinear, making it difficult to model using traditional statistical methods. Neural networks consist of layers of interconnected nodes or neurons that process information and pass it on to the next layer. The output of the final layer is used to make predictions about future values of the time series. To use a neural network for time series analysis, you first need to select an appropriate architecture, which involves deciding on the number of layers, the number of neurons in each layer, and the activation functions used by each neuron. Once the architecture has been chosen, the model needs to be trained using historical data. During training, the weights and biases of the neurons are adjusted so that the model can accurately predict future values of the time series. Finally, the model can be used to make predictions on new data.
Forecasting techniques. Forecasting is an important aspect of time series analysis as it allows us to predict future trends and make informed decisions. There are several techniques for forecasting time series data, including moving averages, exponential smoothing, and ARIMA. Each technique has its strengths and weaknesses, and the choice of technique depends on the specific characteristics of the data being analyzed. Moving averages are a simple yet effective technique for forecasting time series data. They involve taking the average of a certain number of past observations to predict future values. Moving averages are useful for smoothing out random fluctuations in the data and identifying trends. However, they may not be suitable for data with complex patterns or seasonality. Exponential smoothing is another popular technique for forecasting time series data. It involves giving more weight to recent observations and less weight to older observations. Exponential smoothing is useful for data with trend and seasonality, but it may not work well for data with irregular patterns or outliers. ARIMA autoregressive integrated moving average is a more advanced technique for forecasting time series data. It takes into account both the autocorrelation, the relationship between past and present values, and the moving average of the data. ARIMA is useful for data with complex patterns and seasonality, but it can be difficult to choose the appropriate parameters for the model. Overall, the choice of forecasting technique depends on the specific characteristics of the data being analyzed. It is important to consider the strengths and weaknesses of each technique and choose the one that best fits the data. Moving averages. Moving averages is a commonly used technique for forecasting time series data. It involves calculating the average of a certain number of past observations and using this value to predict future values. The number of past observations included in the calculation is known as the window size, and it can be adjusted based on the level of smoothing desired. Moving averages are useful for identifying trends in the data and smoothing out noise, but they may not work well for data with irregular patterns or sudden changes. To select the appropriate parameters for a moving average model, the window size needs to be determined. This can be done through trial and error, or by using statistical methods such as cross-validation. A larger window size will provide more smoothing, but may also result in a lag in detecting changes in the data. On the other hand, a smaller window size will be more responsive to changes, but may also be more affected by noise. Overall, moving averages are a useful tool for forecasting time series data, but should be used in conjunction with other techniques for best results. Exponential smoothing forecasting. Exponential smoothing is a popular time series forecasting technique that works by assigning exponentially decreasing weights to past observations. This means that more recent data points are given greater weight than older ones, which allows the model to adapt quickly to changes in the data. The level, trend, and seasonality components of the time series are estimated separately using different smoothing factors. The final forecast is then obtained by combining these estimates. To select the appropriate parameters for the exponential smoothing model, one needs to consider the level of smoothing required for each component of the time series. This can be done using statistical methods such as maximum likelihood estimation or by trial and error. It is important to note that the choice of smoothing parameters can have a significant impact on the accuracy of the forecast, so it is essential to choose them carefully. ARIMA forecasting. ARIMA Autoregressive Integrated Moving Average is a popular time series forecasting method that models the relationship between past observations and future values. It is a powerful tool for predicting trends in data, and is widely used in finance, economics, and engineering. ARIMA models are composed of three components: autoregression, differencing, and moving averages. Autoregression involves modeling the relationship between an observation and a number of lagged observations. Differencing involves taking the difference between consecutive observations to remove trend and seasonality. Moving averages involve modeling the error term as a linear combination of past errors. To use ARIMA for forecasting, it is important to select the appropriate parameters. This can be done through a process called parameter tuning, which involves testing different combinations of parameter values to find the best fit for the data. The two main parameters in ARIMA are P, the autoregressive order, and Q, the moving average order. The value of P determines how many lagged observations are included in the model, while the value of Q determines how many past errors are included. By selecting the optimal values for these parameters, ARIMA can provide accurate predictions for future values of a time series.
Choosing the right time series model can be a daunting task, but it is essential for accurate forecasting. When selecting a model, there are several factors to consider, including the type of data, the frequency of observations, and the presence of trend or seasonality. For example, if the data exhibits a clear trend, an ARIMA model may be appropriate. On the other hand, if the data has strong seasonality, an exponential smoothing model may be more suitable. Another important consideration is the complexity of the model. While more complex models may provide better accuracy, they can also be more difficult to interpret and require more computational resources. It is important to strike a balance between accuracy and simplicity when selecting a model. Ultimately, the best approach will depend on the specific characteristics of the dataset and the goals of the analysis. Data preparation. Data preparation is a crucial step in time series analysis and forecasting. It involves cleaning, transforming, and organizing the data to ensure that it is suitable for analysis. Without proper data preparation, the results of the analysis may be inaccurate or misleading. The first step in data preparation is to check for missing values and outliers. Missing values can be replaced with imputed values, while outliers can be removed or transformed. The next step is to check for seasonality and trend in the data. Seasonality can be removed by using seasonal differencing, while trend can be removed by using differencing or smoothing techniques. Finally, the data should be scaled to ensure that all variables are on the same scale. Model evaluation. Model evaluation is an important step in time series analysis and forecasting. It involves assessing the performance of a model by comparing its forecasted values to the actual values in the dataset. There are several metrics that can be used to evaluate the performance of a time series model, including mean absolute error, MAE, root mean squared error, RMSE, and mean absolute percentage error, MAPE. These metrics provide a measure of the accuracy of the model's forecasts and can help identify areas where the model may need improvement. Challenges in time series analysis. Time series analysis and forecasting can be a challenging task due to the complex nature of the data. One of the common challenges is dealing with missing values in the dataset. Missing values can occur due to various reasons such as sensor failures or human errors. In order to address this challenge, imputation techniques such as interpolation or regression analysis can be used to fill in the missing values. Another challenge in time series analysis is dealing with outliers or anomalies in the data. Outliers can be caused by measurement errors or sudden changes in the underlying process being measured. To address this challenge, statistical methods such as moving averages or exponential smoothing can be used to smooth out the data and remove the outliers. Additionally, machine learning techniques such as clustering or classification can be used to identify and remove the outliers from the dataset.
Applications of time series analysis. Time series analysis is a powerful tool that can be applied to a wide range of fields, including finance, economics, and engineering. In finance, time series analysis is used to forecast stock prices and exchange rates, as well as to analyze market trends and patterns. Economic time series data can be used to analyze trends in GDP, inflation, and unemployment rates, among other indicators. In engineering, time series analysis is used to monitor and predict equipment failures, as well as to optimize manufacturing processes. One example of a financial application of time series analysis is the use of autoregressive integrated moving average (ARIMA) models to forecast stock prices. By analyzing historical stock price data, ARIMA models can be used to predict future prices with a high degree of accuracy. Another example is the use of vector autoregression (VAR) models to analyze the relationships between different financial variables, such as interest rates and exchange rates. In economics, time series analysis can be used to analyze the impact of policy changes on economic indicators, such as the effect of tax cuts on GDP growth. In engineering, time series analysis can be used to monitor equipment performance and predict when maintenance is needed, which can help reduce downtime and increase productivity. Financial time series analysis. Financial time series analysis involves the study and forecasting of financial data over time. This type of analysis is used to make predictions about future market trends, identify patterns in stock prices, and evaluate investment opportunities. There are different types of financial time series data, such as stock prices, interest rates, and exchange rates, each with its unique characteristics that require specific techniques for analysis and forecasting. For example, stock prices can be analyzed using technical analysis, which involves studying past price movements and identifying patterns to predict future price changes. Interest rates can be analyzed using yield curve analysis, which involves plotting the yields of bonds of different maturities to identify trends and predict future rate changes. Exchange rates can be analyzed using econometric models, which involve analyzing the relationships between different currencies and economic variables to predict future exchange rate movements. Economic time series analysis. Economic time series analysis is a powerful tool used by economists to forecast future economic trends and make informed decisions. Economic time series data includes variables such as GDP, inflation rates, and employment figures, which are collected over time and used to analyze the performance of an economy. By analyzing these variables, economists can gain insights into the health of an economy and make predictions about future economic conditions. There are several methods that economists use to analyze economic time series data, including trend analysis, seasonal adjustment, and regression analysis. Trend analysis involves identifying patterns in the data over time, while seasonal adjustment involves removing the effects of seasonal variations from the data. Regression analysis is used to identify relationships between different economic variables, such as the relationship between interest rates and inflation. These methods are often used in combination to provide a more complete picture of the state of the economy. Engineering time series analysis. Time series analysis is an essential tool in engineering, used to analyze and forecast a wide range of data. This includes everything from temperature readings to machine performance metrics, which can be used to optimize processes and improve efficiency. One example of time series analysis in engineering is in predictive maintenance, where engineers use historical data to predict when equipment will fail and schedule maintenance accordingly. Another application of time series analysis in engineering is in quality control, where engineers use data from sensors and other sources to monitor product quality over time. By analyzing this data, they can identify patterns and trends that may indicate a problem with the manufacturing process and take corrective action before it affects the final product. Overall, time series analysis is a powerful tool for engineers, helping them make more informed decisions and improve the performance of their systems.
Time series analysis and forecasting are critical tools for understanding patterns in data over time. By analyzing the different components of time series data and selecting the appropriate model and forecasting technique, we can make accurate predictions about future trends and events. It is important to note that data preparation and model evaluation are crucial steps in this process, as they ensure the accuracy and reliability of our results. Furthermore, the applications of time series analysis are vast and varied, from finance and economics to engineering and beyond. As technology continues to advance and more data becomes available, the importance of time series analysis and forecasting will only continue to grow.